Okay, so question 54, propose a mechanism for the following reaction. So just a quick aside, these mechanism questions are actually really, really important for you to get the hang of. So these questions are not going to go away. You'll continue to see mechanism questions throughout the rest of this semester, starting here in chapter 4 and moving on into second semester OChem. So it would definitely behoove you to take the time to get used to thinking about how reactions proceed and to really get used to showing electron movement. The sooner you get used to it, the better off you're going to be down the road. So it's definitely worth the time and investment to get used to these and to get comfortable. Okay. So the good thing about these kind of questions is that everything is already known. You know the reagents, you know the reactants. I'm sorry, you know the reactants, you know the reagents, and you know the product. So that's part of the mechanisms question, is that you already know everything that's going in and that's coming out. The hard part is being able to describe the path of how to get from starting material to product. So let's think about this question. We've already kind of talked about this before in chapter 4, and we've talked about acid catalyzed hydration and addition of alcohols. So that's basically all this question is. It's just an acid catalyzed addition of an alcohol. Okay, so the way we're going to go about this is we're going to start off the mechanism thinking about the nucleophile, thinking about electrophile, and showing how we're going to basically end up forming this carbon-oxygen connection. Okay, so first things first, we already know from the context of the chapter that the alkene is going to be our nucleophile, and or if you want to think about it like this, our base. So the first step is going to be our alkene, acting as a base. So we have H2SO4 in solution, and you can either draw it out if you want, or if you want to make it easier on yourself, you can just say H+. Because as soon as you throw this sulfuric acid in solution, it's going to spontaneously dissociate, and the important bit is the H+. So we're going to have our alkene right here. We're going to end up having electrons from the alkene attack the hydrogen ion, and we're going to end up getting a carbocation intermediate, which we've talked about before. So the question then becomes, do you want to put the carbocation on A, or do you want to put the carbocation on B? Now, if you put it on A, you're going to get a secondary carbocation, versus if you put it on B, you're going to get a primary. So of the two, the secondary is going to be more stable, so the secondary is going to end up forming. So we're going to end up getting a positive carbocation here. So now the only difference is that instead of doing this reaction in water, if we did it in water, or H2O, we'd end up getting an alcohol. But the difference here is that we're not using water. We're using an excess of the methanol. Um, the, the difference between the two is actually slim to none. The only difference is that instead of having two hydrogens attached to the oxygen, one of the hydrogen is being replaced with this methyl group. Okay? The key similarity here is that the oxygen in both cases is going to be acting as a nucleophile. So that's the only difference, is that instead of a hydrogen, we have a methyl. Okay. So again, this problem is not being framed in context of water. Water is only going to be minimally present. Okay. So we've got to figure out how to play around with the alcohol. So you have to recognize at this point that you're going to have another nucleophile electrophile interaction. The carbocation is your electrophile, and your water is going to be your nucleophile. So nucleophile will attack the electrophile, so electrons start on the electrons, and they will start on the position or they'll stop on the position that is electron deficient. So that's obviously going to be the carbocation. Okay, so now at this point we've added our oxygen to the carbocation, and we're actually almost home free. At this point, we've accomplished the majority of what we want to do. Actually, I made a mistake here. It should only be 4 carbons. So this is a good lesson. Always count your carbons. So we have 1, 2, 3, 4 here, 1, 2, 3, 4, and I was attempting to add a 5th one, but after I counted, I realized that I made a mistake. Okay, so it's a really easy mistake to make, but it's just as easy of a mistake to correct. Okay, so now One thing that we need to take into account is that we want to make sure that we charge balance from starting material to product. So on the left-hand side of the equation, the overall charge is positive. On the right-hand side, at this point, the overall charge is neutral. So there's something wrong. Something is amiss. So the first thing we need to recognize is that we need that positive charge, and then after that, we can start trying to do formal charge calculations. So there are really only a couple possibilities, and intuitively, you should start looking around the area where you started making and breaking bonds. So let's just go ahead and do the charge calculation for this oxygen. So the oxygen would be 6 for the valence, minus 3 formal covalent bonds, minus 2 lone pairs. So that's going to equal plus 1. So this oxygen should have a plus charge on it. The question then is, how about this carbon? Does it have a positive charge on it? So the question will be answered whether or not we have a carb or a hydrogen attached right here. So let's look back. So starting off on carbon A had a hydrogen. As soon as these electrons attacked the hydrogen, we added the hydrogen to carbon B, and so that means carbon A still has that original hydrogen, and now carbon A still has this original hydrogen. So to answer the question, does carbon A have that positive charge? The answer is no. No, it doesn't. So because the formal charge calculation would say the carbon's charge will be 4 valence minus 1, 2, 3, 4 covalent bonds. So the overall charge on that carbon is going to be neutral. Okay, so now we have charge balance. On the left, we have a positive overall. On the right, we have a positive overall. But that's not what we want. We want to have an oxygen with a neutral charge. So how do we get there? This part is actually really, really easy. Okay, so at this point, you can either show another methanol in solution, because again, we have I made a mistake again. So again, we're not using water. We are using methanol. That's easily fixed. So again, this is actually a really good thing to show the difference between the two mechanisms. There actually is zero difference between the addition of the alcohol and the addition of the water. All I did was replace a methyl group. So now we have an excess of methanol instead of an excess of water. So we can go ahead and use a methanol. So OH, Me. And we can use that excess of methanol to pull off another proton. So we're going to take off this proton. We're going to break this oxygen-hydrogen bond, which you can see is not there in the final product. Okay, so after we do that, we're going to add that second lone pair. So let's go ahead and add that second lone pair. So that second lone pair is coming from this bond right here. So this single bond right here is the source of this final lone pair in the product. Okay, and then also obviously we'll have H, O, M, E, H. Okay, but this is kind of a secondary product. It's not really that important to me, at least. So the important bit is for you to be able to show how you get from this protonated oxygen to the final ether products. Okay, so that's how we can get from the alkene to the final ether. Okay, overall, only a 1, 2, 3 step mechanism, relatively easy as long as you are comfortable with electrophile, nucleophile, and some basic acid-base kind of arrow pushing. Okay, other than that, it's relatively simple.